Hello everyone, I'm Lily Xiao from School of Highway, Chang'an University. In this chapter, we are going to discuss the soil bearing capacity for shallow foundations. The lowest part of a structure is generally referred to as the foundation. Its function is to transfer the load of the structure to the soil on which it is resting. A properly designed foundation is one that transfers the load throughout the soil without overstressing the soil. Overstressing the soil can result in either excessive sediment or shear failure in the soil, both of which cause damage to the structure. Thus, geotechnical and structural engineers who design foundations must evaluate the bearing capacity of foundation soils. Here, the bearing capacity is defined as the force per unit area that the supporting soil immediately below and adjacent to a function can withstand. Depending on the structure and the soil encountered, various types of foundation are used, such as spread footing, mat foundation, piles, etc. We normally divide them into two types: shallow foundation and deep foundation. In a more general sense, shallow foundations are those that the rate of the depth of embedment to width is approximately less than 4. When the ratio is greater than 4, it may be classified as a deep foundation. In this chapter, we discuss the soil bearing capacity for shallow foundations. As mentioned before, a foundation to function properly, we have to make sure two things. 1. Shear failure of the soil supporting the foundation must not occur. And 2. The settlement of soil caused by load must be within a tolerable limit. The first aspect indicates foundation must meet the stability requirement in design, which means the foundation soil must be strong enough to support imposed loads, and the foundation must be safe against collapse under maximum loads. If the foundation soil is bearing a maximum load without shear failure, we call it is in an ultimate limit state. The second aspect relates to serviceability requirement in design, which means the foundation must enter normal service conditions in the service period. The soil has not excessive deformation, including the total sediment and deformation settlement. If the deformation reached to a limit value that affects normal function, we call it is in a serviceability limit state. For the stability requirement, if the foundation reached to the ultimate limit state, the geotechnical system is likely to become unstable, resulting in structural damage locally or globally. To get more clearly idea about this problem, let's say an example about the foundation failure happened in Canada. Transcona grain elevator, which is very typical and has been mentioned in many textbooks. This picture shows an obvious inclination of the building. The west side of foundation sank 7.32 meters, and the east side was lifted up 1.53 meters, while the upper reinforced concrete structure is intact. This diagram depicts the failure mode of the building. The upper building inclined. One set of the subsoil was upheaved. The structure of the foundation was damaged due to the soil slipped along a probable arc shear surface. There are two main reasons for its instability. For one thing, after failure, investigation revealed that there are 15 meters thick of soft clay below the foundation. The actual base pressure on the foundation soil was about 329 kPa, which surpassed the bearing capacity of the foundation soil 277 kPa. It is beyond the stability requirement. For another, the loading speed is too fast. As a result, the pore water can't drain out in time and the soil strength can't be enhanced effectively. In terms of the serviceability requirement, both the total settlement and the differential settlement must be within acceptable limits. What constitutes serviceability limit states? Here are a few markers: unsightly cracks, differential settlement, excessive total settlement, intolerable vibration, intolerable lateral displacement, and rotations. This picture shows a typical example of an excessive differential settlement of a road foundation. The surface is bumpy, and a group of cracks appeared on it. It is out of serviceability requirement, and the foundation failed. Having get the idea of stability requirement and the serviceability requirement, there are two important factors corresponding to them respectively. The first one is the ultimate bearing capacity QU, which is defined as the maximum bearing pressure that the soil can sustain before continuous shear failure occurs. The second one is a lowable bearing capacity QA, which is defined as the working pressure and that would ensure an acceptable margin of safety against the bearing capacity failure. Therefore, the factor of safety to the foundation soil can be defined as Fs equals to Qu over Qa. During the design of buildings and foundations, the factor of safety is usually determined according to their safety level. So, the allowable bearing capacity can be calculated by equation Qa equals to Qu over Fs. Then, how to get Qu? It can be tested by field experiment or calculated according to the relevant formulas. We will detailed explain it in later chapters. That's for today. Thanks for your attention. See you next time.